Okay, folks, this video is going to cover a technique, a pretty cool technique called logarithmic differentiation. Okay, remember back in pre-calc or maybe in intermediate algebra, some course you had to take where you had to learn a bunch of log rules, right? You learn all these log rules and you're thinking like, why do I need to learn these rules? And the teachers give you these big expressions and they tell you to expand the log and so forth. And you're like, when am I going to use this stuff, right? Well, this is where we're going to use it. And so if you learn those rules, good. If not, let me just brush them up real quick. So we've got three basic rules that we want to refer to as far as logs. Don't confuse these with the derivative rules, right? Because there's a product rule, a quotient rule, and a power rule for logs. So maybe I won't write the names down, but these are not derivatives, right? These are just log properties. So if I'm taking the log of a product, let's say log base b of some product u times v, right? Then what I can do is I can split that up. This is one log, but maybe it's of something complicated, right? If I'm combining these things, then maybe that's complicated. So maybe I want to shrink it or shrink the argument or the input of my log. And so the log of a product becomes the sum of two logs, right? So log of u plus log of v. All right, and notice the base doesn't change, and these properties work in reverse too. So if you have two logs with the same base, you can combine them by multiplying the two. If you're adding two logs, you can combine them by multiplying the two arguments like that. So that's one of our properties. Another one is if multiplication inside becomes addition, then what would division inside becomes? And that becomes subtraction, right? We get log base b of u minus log base b of v. So in the context of log properties, sometimes they call this the power rule, quotient property, let's say. And finally, if I've got log base b of, let's say, some argument u raised to some exponent n, then this one almost feels similar to the derivative rule, but again, unrelated to derivatives right now. But the exponent can come down, right? N times log base b of, and we don't decrease it like we do, it goes away, just log base b of the whatever the argument was. Okay, so let's say sometimes we use a combination of these properties. So if we've got a log of something really complicated inside these parentheses, let's say, what we can do is maybe split up some fractions, right? Maybe take some products, break those up piece by piece. Any exponents that we have, maybe we can bring down front. And what we're going to see is that if we apply those things first using a log, then we can go through. We can take our derivative a lot easier. And so that's what we're going to do. And then we'll just tweak it a little bit to get our answer back. Okay? So just a review of these properties. Let's clean up the board. And suppose I've got something like this. Let's say I've got y is equal to, let's say I've got x cubed plus, let's say x cubed e to the x to the fifth power times 4x squared plus 7x to the 9th power. Okay, just kind of made that up on the spot. Okay, let's say I want to take the derivative of this. So maybe I'm calling it y here because that's what I'm going to use for my logarithmic differentiation technique. But let's say it was just called f of x, right? Could I just find f prime of x using our regular techniques? Sure, I could. Let's think about what I'd have to do though. I've got a product here, so I'd have to use the product rule, right? For the derivative of this piece, I'm going to have to use the chain rule because I have that 9 on the outside. So I'm going to have to use a product rule, then a chain rule. For this thing, I'm also going to have to use the chain rule because I have the 5 on the outside. And then I'm going to have to use another product rule within these parentheses because I've got that multiplication. So 2 product rules, 2 chain rules, keep track of everything. And then, so it's possible. For fun, I'm tempted. I'll see how long the special technique takes, but I'm tempted to do that, right? Because I like stuff like that. But we want to try and get a different technique, okay? So we want to find f prime. If I'm calling this y, I want to find y prime. All right. So before I do that, though, I'm just going to go ahead and apply a good old natural log to both sides of this function, or both sides of this equation. Why am I going to do that? at this point, why not, right? I'm just going to do it because I can do it, right? So this thing is the same as that thing. So if they're the same, I can plug them both into some kind of function and the result will be the same. That's fair. So let's just try that. So let's just say natural log of, let me just save some space. I've got y is equal to that expression. So I'm going to claim that natural log of y is equal to natural log of this entire expression. Right, get it around with some kind of square brackets. Okay, great. What can I do now? What can I do here? Well, I want to find y prime eventually. Let's not forget that. Make a little note. Find y prime. Okay, so at some point I want to find y prime. Let me, though, before I start taking derivatives, using implicit differentiation over here, let me just start using some y properties and see what I can do. So natural log of y is equal to, I'm just going to convert the right-hand side as much as I can. So first of all, I've got the natural log of a product. Right, so I'm going to kind of break these up step by step. I've got natural log of this thing times that thing. So that can become natural log of the first, x cubed times e to the x to the fifth, plus natural log of the second piece, 4x squared plus 7x to the ninth. All right, no big deal. Just log of a product, boom, boom, equals the sum of two logs. There we go. What can I do next? I can bring this 5 down, right? I've got a log of something to the fifth, and then I've got a log of something to the ninth. So I can bring both exponents down. So let's do that too. So let's say 5 times natural log of x cubed times e to the x plus 9 times natural log of this, 4x squared plus 7x. Okay. Can I go any further? So first of all, to note, within this log, I can't go further, right? I've got 4x squared, which is a product, 4 times x squared, right? So there's a little product. I've got 7 times x, so that's a product. But this term, if I'm thinking 4x squared right now is glued together as one term, 7x is glued together, they're being added within the log. Remember, there was no property that allowed me to break that up. So I cannot break that up, so that thing is there to stay until we start taking derivatives. However, here, I've got a multiplication. Okay, that's a product. So I can go ahead and break that up. Notice 5 times this log. When this log turns into a sum, I'm going to have to multiply the entire sum by 5. Okay, so that's got to get distributed. An alternative method would have been to distribute this 5 across this multiplication right off the bat and got x to the 15 times e to the 5x. I'm actually thinking that might have been easier, but that's okay. Let's just leave it like this. So let's go forward. Equals 5 times, and now I'm going to break up this log into natural log of x cubed plus natural log of e to the x. All right, and close up those brackets. Now that all gets distributed a 5 through there, plus this guy is how he is. 9 times natural log of 4x squared plus 7x. All right, there we go. And so that's, is that as simplified as possible? Let me save some time. No, let me just rewrite it. Here I've got 5 times inside these parentheses. Now I can bring the 3 down on this log. So I've got 3 natural log of x. So therefore, this guy, natural log of x, is as simplified as it can be, right? No more simplification than that. Natural log of e to the x is actually equal to x. Right, that's an inverse property right there, because this is log base e of e to the x is x. So there we go for that. And over here I've got plus 9 times that log. So this guy has not been changing since earlier. And the last thing I could do is distribute this 5. All right, so I'm going to get 15 natural log of x plus 5x. Let's think back to what I said earlier I could have done. If I squeeze this 5 in there, I'd have 5 times 3, let's say, multiply those exponents. Here I'd have a 5x, and then if I were to take the derivative, then this 15 would have come down out front, which is what I'm going to form once I distribute this 5 in. And then I would have had natural log of e to the 5x, which would have been equal to 5x, which is what I'm going to have when I distribute that guy in there. All right. Anyway, so let me erase all this work, but notice what we've done. And so it's debatable, before I go on, it's debatable what's easier and what's not, right? Remember, I described how we could have taken the derivative originally, right? Jump in, use product rule, use quotient rule, use another product rule. Did I say quotient? Whatever. But it was a mess. This, also a mess, right? So kind of messy. However, the differentiation process, taking the derivative of this, is going to be super nice. That's what's cool. So let me erase all these steps up to our final answer. I'm going to leave that because that was sort of our original function. And at this point, what we essentially showed is that natural log of y is equal to this. 15 natural log of x plus 5x plus 9 times the natural log of this piece, which we were not able to disintegrate or break up any further. Okay, so we've got that. Okay, let us take derivatives, right? We had y of a function of x originally, right? We put these natural logs here, but we had y was equal to this function of x, so we want to take the derivative with respect to x. So how do we do that? Let's just apply d dx to both sides of this equation. So I'm going to say d dx of the left-hand side equals, let me squeeze this in here, the derivative with respect to x of the entire right-hand side. All right, so now let's let the fun begin. So first of all, here we've got the derivative of, with respect to x of natural log of y. We want to say that's the derivative with respect to y of natural log of y, and then multiply that by dy dx, right? Our usual chain rule application that happens when we're doing this implicit differentiation. And lo and behold, we've got the dy dx, which eventually we're looking for, right? Find y prime. Right, that's our goal, find y prime. So we found it, we've just got to solve for it, uncover it. Okay, so we've got that. On the right-hand side, let's see what we've got. So first of all, I'm taking the derivative of across plus signs. We know I just go term by term by term, right? So rather than rewrite everything, let me just go ahead. What am I doing here? I'm doing the derivative with respect to x of 15. I say I'm not going to do things and then I do it. We're going to do the derivative with respect to x of 15 natural log of x, right? Then we're going to say plus the derivative with respect to x of 5x. And then we're going to say plus the derivative with respect to x of 9 times natural log of 4x squared plus 7x. There we go. Clean that up a little bit or make myself feel a little bit better. About showing this step by step. And actually that reminds me of some other steps that we can do, right? In other words, here, constant multiple, I can pull all these constants out in front of the derivative. So this is really 15 times the derivative with respect to x of natural log of x, right? Plus 5 times the derivative with respect to x of x, right? Plus 9, pull this constant out front, times the derivative with respect to x of that thing, 4x squared plus 7x, okay? And now what we're going to see is most of these things that I'm taking the derivatives of, here I have a natural log, we know it's derivative, right? And then these are polynomials, we know the derivative is really easy. And so, yeah, there was a lot of setup, there was a lot of preamble to get here, but now the differentiation process is easy, right? So what do we have? We have 15 times, the derivative of natural log of x is 1 over x. So we get 15 times 1 over x, or you might just call that 15 over x. We have 5 times 1, right, out of that. If you had just left it up here without playing around with our constant multiples, you just say, what's the derivative of 5x? The answer is 5, right? So maybe we'll just call it that. And what's going on over here? Little chain rule. So we're going to do a little chain rule. I've got plus 9 times the derivative of, actually, I'm sorry. I was thinking we had logs involved. No chain rule. 8x plus 7. Right? There we go. Cool. So let's clean this up a little. I've got 15 over x plus 5 plus 72x plus 63. And 63 and 5 makes 68. Squeeze that in here. All right, there we go. Okay, are we done? Not quite. And that's where this stuff is going to get even messier. All right, so let's see what we've done here. I'm going to erase all the work proceeding to our final answer again. Okay, so we originally had y is equal to that stuff. We applied the natural log to both sides. Let me demonstrate what we've done here. Natural log like that. So we applied natural log to both sides, but what we see up there in black was our original equation. From there, we differentiated, we first expanded all of our right-hand side using all our log properties, broke it down. Then we took derivative with respect to x at both sides. So we used implicit differentiation over here. So actually, we've got to argue what this is. And then we've got the y prime over here. So let me clean that up a little bit, then erase some of this stuff and finish up. The derivative with respect to y of natural log of y, well, what did we do over here? The derivative with respect to x of natural log of x was 1 over x. So here we're going to get 1 over y. All right, 1 over y is what that expression was, times, what are we looking for? dy dx, or call it y prime. Okay, so 1 over y times y prime is equal to all these lines, which we finally summed up to that. So let me scoop my final answer up top a little bit. Let me rearrange the terms just for fun. We're going to write 72x plus 68 plus 15 over x. Just kind of move those terms over. All right. But what do we want to solve for? We want to find y prime. Here I've got 1 over y, right? Because we had that little chain rule, introduce this 1 over y. So how do I isolate y prime? Let's multiply both sides by y. So times y, wrap this in parentheses, and times y. All right. And now, so y over y, this cancels, goes away to a 1. So what we've done is isolate y prime. And over here I've got y. What's y? Let me get rid of that natural log. And y was our original expression. So a weird phenomena of this process is the original expression becomes part of our answer. So I've got, I guess we don't need the brackets here because there's just multiplication there, but I've got x cubed e to the x to the 5th times 4x squared plus 7x to the 9th. Okay, magic? Maybe. Was that long? A little bit long. Would it have been quicker to try to just jump in and do it the old-fashioned way without this technique? Maybe, okay? But this technique is out there. Sometimes it's helpful. If you've got quotients, it might be helpful. So yeah, so you got an example here. There's one more type of function where we sort of need to use this technique. So this sort of polynomial technique, well, I had the e to the x in there for fun. But this went relatively smoothly, but we could have done it other ways. There are functions where you can't do it other ways. So I will do one more video with one of those functions. And you can see how that works. I don't know about you, but I'm tempted to do it the other way. Let me just mention, no, that's not F prime. If you do it the other way, meaning just straightforward, use a product rule, go forward from there, your answer probably won't look identical to the way we just got it, right? Because the way we just got it had the original terms there, right? And they're not going to live there in the same sense, although they might. So maybe look at it. I'm really curious. How would we do this? If I wanted to find f prime here of x, I need the derivative of the first one times the second one, right? So the derivative of the first one is 5 times that thing to the 4th times the derivative of the inside, which is a product rule. So then we're going to get 3x squared e to the x plus x cubed e to the x, right? That's my derivative of that. This is the derivative of that. Okay, so we have the derivative of the first function. It's all product here, so I don't have to worry about parentheses, times the second function, 4x squared plus 7x to the 9th, plus the original first function, x cubed e to the x to the 5th, times the derivative of the second one, which we don't have another product rule inside, so here we're going to get 9 times that thing to the 8th times the inside derivative, which is going to be 8x plus 7. Okay. Is this the same as what we had? I don't know. Challenge yourself. Do it. Yeah. Some things are going to look a little bit different. So the previous one had a 15 over x, right? A 15 over x somewhere. And that's a little bit weird because none of this has any x's in the denominator. So you might be saying, how are those things how is it really going to equal out? But remember, we had that 15 over x plus some other terms. But then we were multiplying that back by the original function, which has x's present, right? So I guess some of those x's cancel that one. So that's kind of some of the weird stuff that might happen behind the scenes. Anyway, though, you've got this if you want to try to simplify, try to work with both of them, see what you can do. But anyway, that's our technique of implicit differentiation. I'm sorry, logarithmic differentiation.